What happens if the two samples actually come not only from completely different distributions, but they're not paired anymore, which is to say that you might have a different sample size from both populations, and there isn't a simple way or clear-cut way to link one observation from the first sample to another observation from the second sample. So let's say you have n observations that have been taken from a normal population with unknown mean mu1 and unknown variance sigma 1 squared, and then you have m observations that have been sampled from another normal population with unknown mean mu2 and variance sigma 2 squared, both populations being independent of one another. Now it's conceivable that mu1 would actually be equal to mu2 and that sigma 1 squared would be equal to sigma 2 squared, so that in practice you may actually be sampling from the same distribution, but a priori that's not the case. You still want to test the null hypothesis that the means of the two normal populations would be equal against the alternative that they're not equal, but because they're not paired anymore, you can't really look at their differences in the same sort of way. You'll let x bar be the sample mean of the observations from the first population, y bar be the sample mean of the observations from the second population, and their observed values will again be denoted by the lowercase letters, little x bar, little y bar. If sigma 1 squared and sigma 2 squared are in fact known, then you're working with a population with known variance, hence you will be using the standard normal distribution Z after having done an appropriate transformation in order to get a Z statistic. So you still have your null hypothesis, mu1 being equal to mu2, and then depending on whether you want to test for the alternative that mu1 is greater than mu2, mu1 is smaller than mu2, or mu1 is different from mu2 except you don't know in which direction, then your critical regions will be given by the sample statistic Z0 being greater than Z alpha, being smaller than minus Z alpha, or an absolute value being greater than Z alpha divided by 2 for some confidence level alpha. And the Z statistic here, the test statistic for that specific case, would be x bar minus y bar. Really, you'd be adding here minus mu1 minus mu2, but you're assuming under the null hypothesis that mu1 is equal to mu2, so you're subtracting 0, so we might as well not put it in there, divided by, this is a different sort of expression than what we've seen before. It's the square root of sigma 1 squared divided by n plus sigma 2 squared divided by m. We would call this the pool standard deviation. And it's some way to combine the sigma 1 squared divided by square root of n that you would have if you only had the first population, and the sigma 2 squared divided by m that you would have if you only had the second population. Now you have both of them together. You have to find some way to express what that variance denominator here would be. So this is the way we do it when we know what sigma 1 squared and sigma 2 squared are. And your Z alpha, these are the critical values. We've seen them before, right? The critical values of the standard normal distribution. And the corresponding p-values are the same. You compute it in the same way. In the first alternative, you look for the probability that Z would be greater than your test statistic Z0. In the second alternative, you look for the probability that Z would be smaller than your test statistic Z0. And in the third alternative, you're looking for twice the minimum value of these two probabilities that you've computed. So that hasn't changed. The critical regions haven't changed. All of this is the same as what you're working with when you're working with known variances. What has changed, though, is the way you compute the test statistic. Here's an example that might illustrate how this would work. You'll sample 100 Albertans, and then you get a sample mean income for that population of 33,000. You sample 80 Ontarians, different number, unpaired. There isn't like a one-to-one match between a given Albertan and somebody from Ontario. These 80 Ontarians have a sample mean income of $32,000. From previous studies, we know that the population income standard deviations are respectively $5,000 in Alberta and $2,000 in Ontario. So there isn't as much movement between incomes in Ontario as there would be in Alberta, based on this kind of information. So given the data that you've collected, would you feel comfortable concluding that Albertans earn more than Ontarians do on average? Because your sample of 100 Albertans gives you a higher sample income in the mean than a sample of 80 Ontarians do. Is there enough evidence here? Yeah. The standard deviations will play a role, and the sample sizes will play a role. We're testing for the null hypothesis that there is no difference between the mean income in Alberta and the mean income in Ontario, mu1 and mu2, against the alternative hypothesis. What we're trying to show is true, that the population mean, that the mean income in Alberta is greater than the mean income in Ontario. That is what our data seems to suggest. The observed difference between the sample means is 1,000, x bar minus y bar, and so the observed test statistic would then be x bar minus y bar divided by the square root of sigma 1 squared divided by n plus sigma 2 squared divided by m. And all you need to do, once you've remembered what test statistic you're supposed to be computing for this unpaired test, is to replace x bar, y bar, sigma 1 squared, n, sigma 2 squared, and m by the values that you've been given. If you do so, you will get that the Z statistic for this comparison are 1.82. The p-value that you're computing is the probability that the difference in the means is greater than 1,000. That's the probability that your standard normal distribution would take on values greater than 1.82. And if you go to the table, you will find that this is 3.5%. So you would reject the null hypothesis when alpha is equal to 0.05, but not when it is equal to 0.01, say. At the 5% confidence level, you have enough evidence to suggest that Albertans make more on average than Ontarians do, but not at the 1% confidence level. In other words, if you're going to think about this as confidence intervals, the 95% confidence interval for the true difference between mu1 and mu2 does not contain the value 0. And so mu1 minus mu2, you're 95% certain, with the caveat that we're talking about certain in the sense of the confidence interval, mu1 is greater than mu2. At the 99% confidence interval level, for what you have computed here, 0 is in there. So it's conceivable that mu1 minus mu2 would actually be equal to 0. We can't reject the possibility at the 1% level. This is really what this is saying. If you do not know what the underlying variances are, but you have small samples, then your critical regions will be defined with the help of a student t-distribution with n plus m minus 2 degrees of freedom. Okay, so you have to take into account the sample sizes in both cases. The corresponding t-statistic, still x bar minus y bar, but now you don't know what sigma 1 squared and sigma 2 squared are, so you will replace that by what we call the pooled variance, sp squared, divided by n plus sp squared divided by m. That form hasn't changed much. Sp squared takes on a very specific form. It's sort of a weighted average of the estimated variance in the first group and the estimated variance in the second group through the samples. So n minus 1 times the sample variance of the first group of observations, the observations that came from the first population, plus m minus 1 times the sample variance of the observations in the second group divided by the total of these two coefficients, n minus 1 plus m minus 1, that gives you n plus m minus 2. And T alpha, that's the critical value for the student T distribution with n plus m minus 2 degrees of freedom. Everything else is the same as what you were doing when you're working with unknown variances. All the z's have been replaced by t's, and you have to have a certain number of degrees of freedom. In this case, specifically for the unpaired tests, the degrees of freedom are n plus m minus 2. And if you think of these degrees of freedom as representing the number of things that had to be estimated before you could do the computation, Well, you had to estimate S1 squared with the data that was available from the first population, and that requires you estimating X bar, right? Because S1 squared is given in terms of X bar, not mu1, the true population. So you've estimated one quantity, and in the second one here, you need to estimate Y bar to be able to estimate the sample variance. So you've estimated a second quantity. So in total, you have N plus M samples, N from the first population, M from the second, but you had to estimate two quantities along the way to be able to compute this pooled variance. And this is why you are dividing here by N plus M minus 2. You've lost 2 degrees of freedom in the process of computing the pooled variance. Here's your example. You have a researcher that wants to test whether on average the new fertilizer that she came up with yields taller plants. So you divide the plants into 2 groups, a control group, which will be treated with the old fertilizer, and a study group, which you will treat with the new fertilizer. And you get the following data. The sample size of the first group is 8. The sample size of the second group is 8. Here it happens that M is equal to M, but that's not usually the case. That's certainly the case here. The sample mean in the first group was 43.14 for the height. The sample mean in the second group was 47.79. And you have a sample variance of 71.65 and 52.66 respectively for the first and second group, for the control group and the study group. And you're trying to test the null hypothesis that the new fertilizer that she came up with has no effect versus the alternative hypothesis, based on what you're seeing here, based on what she wants to prove really, she claims, is that the second fertilizer, the new fertilizer, is more effective than the first one. And so the second population mean, mu2, should be greater than the first population mean. That's what she wants to test for. So if you assume that the null hypothesis holds, that mu1 is equal to mu2, you need to compute the observed difference between X bar and Y bar. That gives you minus 4.65. Right? So we get an improvement of 4.65 units of height on average. You compute the pool sampled variance, N minus 1 times the sample variance in the control group plus M minus 1 times the sample variance in the study group divided by N plus M minus 2. You replace all the values in there and you will get, well, that this thing here is about 7.88 squared. Pooled variance, 7.88 squared. The pool standard deviation would be 7.88. And should we call this the pooled sample standard deviation and the pooled sample variance? Now you compute the test statistic for this because you didn't know the sigma squares, the variances. You estimated them using the pooled sample variance, X bar minus Y bar divided by the expression you get here. And if you do the computation, you work it out, you will get that this is minus 1.18. So your p-value, the probability that the difference is smaller than minus 4.65, would be the probability that the t-distribution with 14 degrees of freedom would find itself below minus 1.18. Right? That's only true under the null hypothesis for that specific situation. And because in the book or in the table, you only look at critical values on the other side, well, you realize that this is the same thing as the probability that the student distribution with 14 degrees of freedom would be greater than 1.18, and then the values in the table will show you that this falls between 0.1 and 0.25. Yeah, you need to know how to get that information from the table. You need to know how to get this 1.18, so you need to know which formula to use here. So you need to know how to compute the pooled variance, obviously. But once you have this, and you know what the degrees of freedom should be, you need to be able to identify the interval in which this quantity falls, this probability, this p-value. And what this is telling us is that at either the 5% confidence level or the 1% confidence level, we could not reject the null hypothesis. We're not able to say with certainty that the new fertilizer is an improvement or produces taller plants than the old fertilizer on average. in terms of the confidence interval, what we have shown, this is x bar minus y bar, the observed difference, minus 4.65. What we've shown is that 0 belongs to both the 95% confidence interval or the 99% confidence interval. This is the confidence interval from mu1 minus mu2. And hence, it's conceivable that the true value of mu1 minus mu2 is 0. Right? How do we find these interval endpoints? Well, we had a number of degrees of freedom. We knew it was 14. And we knew what the actual value that interested us was is minus 1.18. Or 1.18 because we're looking at the mirror image of this. So we look through the row for 14 degrees of freedom until we find two successive quantities that sandwich our value of 1.18. There it is. And that gave us an alpha here of 25% and an alpha of 10%. If we wanted to be certain that the 1% confidence level, we would have had to have a computed value for the test statistic here falling between 2.624 and 2.997, or anywhere to the right of 2.624 would have done the trick. In the third case, if you don't know what sigma 1 squared and sigma 2 squared are in the underlying populations, but the samples are large, then you can revert to the standard normal distribution. Right? For large samples, the student t distribution converges to the standard normal distribution. Compare that to this here. It's not quite the same computation, right? In the first case where you knew sigma 1 squared and sigma 2 squared, when you compute your Z statistic, you're going to be using sigma 1 squared and sigma 2 squared. Now you don't know what sigma 1 squared and sigma 2 squared are. So you can't use sigma 1 squared and sigma 2 squared, but if the samples are large enough, what this is saying is that you can actually use the estimated sample variances from the samples in both populations instead of the known variances from these populations, and then you can just use the Z statistic and the standard normal and work through these quantities instead. How large is large? Large is large enough. 8 is small, 100 is probably large enough. 30 is often used as the cutoff point, but it really depends on the situation, and it does depend on the value. So if instead of 8 observations we had in each group here, we had 100 observations in each group, but everything else stayed the same sample mean and the same sample variance, we would still be testing for the null hypothesis. mu1 being equal to mu2, there being no effect when you use the new fertilizer, versus the alternative that the new fertilizer tends to give rise to taller plants, mu1 being smaller than mu2. So the observed difference hasn't changed, it's still going to be minus 4.65. Now the observed test statistic will change because x bar minus y bar doesn't change, s1 squared, s2 squared doesn't change, it's still the same quantities that you had, but n and m do change. You're dividing by larger values here. You have more observations, you're more sure about the distribution in each group, so to speak. And so the Z statistic has a value of 4.17 or minus 4.17, the corresponding p-value. The probability that the difference would be smaller than minus 4.65 is very, very small if the null hypothesis held, right? So the probability that the difference would be minus 4.65 or less, what it is that you've observed as a difference by chance, because this is what would be happening if there isn't an actual effect. If this is happening by chance, it's basically nothing, 0. You're like 4 standard deviations away from the mean in the standard normal. That's just not going to happen. Here you would reject the null hypothesis. At either the 5%, 1%, even at the 0.1% level, you would reject it. Okay? So if you get the same results in terms of the sample mean and the sample variance when you've taken 200 samples as opposed to 16 samples, well then you know for a fact that the difference that you've observed is quite likely to be significant. The sample size is really what drives these things. At least in many instances it is. If you make sure that your studies have enough samples, you'll probably be able to show what needs to be shown. The problem is that in many real cases, obtaining the measurements for the sample is quite costly. And so now you have this battle between, we want as many samples as possible so that the power of the test can be very high, but we need to minimize the cost of obtaining our samples. And very often it is money that talks. And so you'll take as many measurements as you can afford to take measurements. But then it might turn out to have been all for naught because you don't have the kind of power you want. You didn't have enough observations.